Okay, hello everybody, welcome to question 2. Let's begin. Okay, so basically we're going to do the same thing as we did in question 1 and find the Fourier series of this particular figure, or the signal inside this particular figure. Okay, so we're going to go through the same set of questions and from that work out what A0, AN and BN are meant to be. Okay, so take a good look at the signal. Okay, and answer this question. What is the period of S2 of t, and what is the fundamental frequency F0? Okay, so again, the period is the duration by which the signal repeats itself, and in this case, if I set my reference to -0.5, okay, the corresponding point here is on this side, so from -0.5 to 0.5, the period there is 1. Okay, so let's write that down. Correspondingly, the fundamental frequency is the reciprocal of the period, so that's also equal to 1 Hertz. Okay, so let's write 1 second here. Alright, good. Okay, so B, what is the DC component of the signal? Find also A0. So the DC component is basically the offset of your particular signal, or your average value, if you like. So if you simply just eyeball this particular waveform, you'll notice that across one period, that area there should be the negative area. It should match up exactly with that area, okay, giving you a net area equal to 0. So we expect the value of A0 to actually equal 0. Okay, so we'll actually go ahead and compute A0 and see this is actually the case. But before we do that, let's also take a good look at this particular function. This is a linear function, so S of t, S2 of t, is a linear function, okay, between duration -0.5 to 0.5, that has a y-axis intercept at 0 and a gradient of 1. Okay, so if you go delta y on delta x, this gradient will equal 1. Okay, so let's get to it and calculate A0. So A0 is your average value across one period. Okay, and again, it's irrespective of where I begin my integral, as long as it's over one period. Now, in this particular case, it makes sense for me to start over at -0.5. Because if I go from -0.5 to 0.5, this is just one integral that I need to take care of. This is one continuous function. However, like, I could have equivalently gone from 0 to 1. That could have worked as well, except in this case, it would mean that I have to do the integral over two parts. I have to go 0 to 0.5 and then 0.5 to 1. But I could have done that also. You'll get the same answer. But today I'm going to go from -0.5 to 0.5 and basically work out that integral. Okay, so, and also at the same time I'm just going to fill in these values as well. It will simplify the integral. So we're going to go from -0.5 to 0.5. The t value was equal to 1, so I didn't write that down. S of t was equal to t, and that's integral of t between -0.5 to 0.5 t dt. Okay, so integrating this, I'll get t squared on 2. Remember, you add 1 to the index, divided by the new index. Okay, so don't forget your limits. Now we have upper limit minus a lower limit. Upper limit minus a lower limit. So this particular calculation, fine, it works out to 0. And that's what we expect, because the average value, like we saw before in the diagram, area, this has a net area equal to 0. Okay, good. Let's go for part C. If S2 of t an odd function, well, let's have a look. An odd function has to satisfy S of t equal to negative s of negative t. Okay, so basically what this is trying to say is it has rotational symmetry about the origin. Okay, so if you imagine picking up that side of the function, so between 0 to 2.5, picking that up and rotating it 180 degrees over here on this side, you'll find that it lines up. So whatever's on this side will occur on the negative down here. Okay, it's rotational symmetry. Okay, that's what we call an odd function. So yes, in this case S2 of t is an odd function. And so from there, let's see what we can say about an and bn. Okay, so now remember you from just before, an, in the overview, we said that an corresponds to the coefficients or the cosine basis functions. Okay, and the cosine basis functions represents the even functions, whereas the sine basis functions represent the odd functions. Now, if S2 of t was completely odd, then we can say that A0 should evaluate to 0, because there will be no even components in this particular signal. Okay, so we're going to go ahead and calculate an and actually demonstrate that this goes to 0, and we'll expect some values for bn. Okay, so let's go ahead and calculate that. So we have an that we need to find. Let's do that first. So yes, it is odd. Okay, D. Let's calculate an first. Okay, so I've just written down the definition. Let's go ahead with the integral. So it's going to be 2 integrate between -0.5 to 0.5. T was s of t was just t. So it's cos 2 pi n. Instead of writing f0, this is equal to 1. So I'm just going to imply a 1 here, and let's just write 2 pi nt dt. Okay, so basically this is our an calculation we have to make. This is an integration by parts. So if you remember from your maths, this is integral of v dash u is equal to uv minus the integral of u dash v. Okay, so that's integration by parts. I'm going to let my u equal to t, and so my v dashed would be equal to cos 2 pi nt. So we have to find the u dashed value. So differentiating t just gives me 1. Okay, t different ddt of t equal to 1. And then here we're going to integrate. So a cos goes to a positive sign, but we have to take the derivative and divide by the derivative of the inside. Okay, so that is my v. Alright, now going ahead with integration. So first I have to write u times v. So u times v, that gives me, so I'm going to write my 2 here. Going ahead with the integral, so it's u times v, so it's going to be t times sine 2 pi nt divided by 2 pi n. So this is my u times v business, so don't forget your limits. Okay, so that's the first bit. Then I have to do the second bit. Okay, so this is now minus, and don't forget the 2 out the front, so I'm going to leave that here. And this is the integral, don't forget the limits. Okay, of now this is u dash v. So u dash is here, v is here, and multiply them together. By 2 pi n dt. Good. So that's basically what we have. Okay, so let's simplify this a little bit more. Okay, I'm not going to touch this. Let's just finish off the integral first. Okay. let's just finish the integral. Okay, so yeah, it might be a good idea actually for me to pull this out before I finish this integral. So let's pull that out first. So taking this outside, the 2's will cancel, leaving me with 1 on pi n. Okay, so now integrating this. Sine goes to a negative cos 2 pi nt divided by 2 pi n. Alright, good. And of course, don't forget your upper and lower limits. Alright, so now once we get this far, let's just go ahead with algebra and then work out this definite integral. Alright, good. So what I might do is I'm going to take a copy of this, run out of the page. Let's go to the next page. So this is the expression I'm going to work with. So let's just go with that. Okay, so let's continue. I'm going to factorize this outside. So I'm going to get 1 on pi n. Okay, upper limit minus a lower limit. So that's going to be 0.5 out here. Sine, substituting 0.5 in for t. So 0.5 times 2 gives me 1. Gives me pi n inside the argument. Okay, next, minus the lower limit. Okay, minus the lower limit. Now, negative 0.5 is now in for t. So negative 0.5 here. Okay, multiplied by sine, again, negative 0.5 in for t. So that gives me negative pi n inside the argument. Okay, so that is basically that bit here. So I'll just close the bracket. That's that bit there. Okay, let's continue over this side and work this out. And also, I'm going to pull this denominator outside. So I'm going to get here negative 2 pi squared n squared. Okay, and upper limit actually I'm not going to do that yet. I'm going to take this outside and put it here. Okay, so this becomes a positive cos 2 pi nt. So I haven't done the upper and lower limits yet. I'll do that on the next line. Okay, and I'll also clean this up a little bit so we have more room to work with. And you might already notice this can be simplified, expanding the brackets. Okay, so before we do that, negative times negative, it gives you a positive, but don't forget that negative sign here. Sine, the sine function, remember, is an odd function. So if we were to remove the negative sign from inside the argument, you have to append the negative sign here. So in actual fact, we have 3 negatives, so we actually end up still negative. Sine pi n. Okay, so that, yeah, you can also say this, but it equals, this part will equal 0 anyway. Okay. Anyway, now let's finish this off. So upper limit minus a lower limit, substituting upper limit inside. So we have here cos of, substituting that one in, so that's pi n, upper limit minus a lower limit, leaving us with that. Okay, good. Let's keep going. See what we get. Okay, so as I said, we're expecting these to come to 0, and this is the reason. For our sine function, okay, sine looks like that. This is 0, that's 2 pi here. This is pi. Okay, so for every integer value of pi, remember n is always going to be integer. Okay, so for every integer multiple of pi, notice what happens to the sine functions. It always lands on 0. So that part's going to go to 0, and so is that part. Okay, that's what's happening here. Okay, so all of that part we expect to go to 0. All of this. Now, cos is an even function. So when I take out the negative sign, we don't have to change the sign here. So this is equivalent to saying cos of pi n. And look at this, because these are equal, of course they subtract equal 0. And this is what we expect, because originally we saw, okay, this function is purely odd. And so if it's purely odd, we do not expect there to be any even components in it. So the even basis functions, which are the cosine functions, the even bases, yeah, they're not going to exist. They're all zeros. That's what we see here. So an is always going to be 0 in our case. Let's go and find out what bn is going to be. So remember, now this is a purely odd function. We expect bn to actually come out with an answer, with a number. Okay, so let's have a look at that. I'll start a new page because I'm expecting this to be long. Okay, so calculation of bn. Good. Just the definition. I'm going to fill in all the details that I know. So t is equal to 1, and I'm integrating over one period from negative 0.5 to 0.5. And I'm also going to fill in the value for f naught, so that this integral turns into negative 0.5 to 0.5. S of t is t sine 2 pi n t dt. Okay, so remember, this is another integration by parts, so very similar to before. I'm going to let u equal to t and my v dash equal to sine 2 pi n t. So I have to find my u dashed is equal to 1, and my v is the integral of this, so sine goes to a negative cos, and of course remember to divide by the derivative of the inside. Okay, good. So let's carry out with the integration by parts. The first bit is going to be your u times v. So it's going to be a negative t cos 2 pi n t on 2 pi n between the limits of negative 0.5 to 0.5. That's our first bit. And then remember, we have to subtract, don't forget the 2, subtract the integral now of v dashed u. So in the limits, u dashed v. Okay, so I'm going to get here negative, I'm just append that in the front, cos 2 pi n t on 2 pi n dt. Okay, so I'm not going to do anything with the first bit. I'm just going to go ahead and evaluate this integral here. Okay, but before I do that, I'm actually going to factorize this as well. So let's do that first. I'll leave the 2 as is. And, okay, so we're going to factorize that outside. So 2 will cancel with the 2, leaving me with 1 on pi n. So 1 on pi n. And then I'll do the integral. So integral of the cos turns into a positive sine 2 pi n t. And of course divide by the derivative of the inside and fill in the limits. Okay, now that we've got that, get that part, we can go ahead with the rest of the algebra. Okay, upper limit minus a lower limit. And of course I'm going to pull the denominators out if I see fit. Okay, so 2 goes with that 2, leaving me with pi n, factorize out the denominator. And at the same time, I'm going to switch the limits. I'm going to deliberately make that positive and flip these limits. Okay, same thing with here. I'm going to factorize this outside, leaving me with pi squared n squared. So 2 pi squared n squared in the denominator. Okay, and this I'll leave alone for now. Alright, good. Now that we've simplified this, it should be easy to deal with. So let's go ahead and go upper limit minus a lower limit and see what we get. So bn is equal to 1 on pi n. Upper limit, negative 0.5 cos negative 0.5 in there gives me negative pi n. Okay, upper limit minus the lower limit, so that's going to be 0.5 cos pi n. Okay, upper limit, lower limit, that's that part. Okay, so that's good. Let's continue over here and work out this bit, 2 pi squared n squared. Okay, again, upper limit minus the lower limit, so substituting 0.5 in here, I get sine of sine of pi n. Okay, 2 times 0.5 gives you 1. So this is going to be sine of pi n minus the lower limit. So that's going to be sine of negative pi n. Okay, good. So let's see what we get. Okay. Okay, so let's ignore this bit for now and come over here. Remember what we said for sine. Okay, for every integer pi, basically any integer, for every integer multiple of pi, sine will go to 0. So this is 0, pi, 2 pi, and so on. So that part goes to 0. And over here, this is the same thing. In fact, if I took out this negative sign, put it here, sine, remember, it's the odd function, so I can do that, but I have to change the sign to positive. And look over here, it's the same thing. Okay, sine of an integer multiple of pi, that one also goes to 0. Okay, so this entire term here should disappear. It's all 0. It's all equal to 0. Okay, how about this bit? Well, let's clean it up and see what we get. Okay, so I have 1 on pi n. Now, cos is an even function, so I can get rid of that. No consequence. Okay, so I have here, looks like grouping the like terms will yield negative cos pi n. So, and this is 0, so I don't have to write that down. So basically, the expression I get left with, negative cos pi n on pi n. Okay, and well, I better go through this in more detail so you can appreciate it. So this is a cosine function. Okay, this is your value of pi here, this is your value of 2 pi. So for every integer multiple of pi, notice what happens. So I have here cos of pi, cos of 2 pi, cos of 3 pi, and so on. So if you like, this controls whether or not it's a positive or negative sign. And the remainder down here, that controls the amplitude. Okay, so that, if you like, this expression here gives you your Bn. Okay, so if I was to summarize, A0, we found that to be 0. An, we found that also to be 0 because this is a purely odd function. And finally, Bn was equal to negative cos pi n on pi n. Okay, so that's good. We just computed that. Let's have a look at the final part of the question. It asks us to use f_series.p function to plot and check my result. Okay, so over here, I've gone ahead and done that. So let's change the fundamental frequency. We saw that for this particular question, going from negative 0.5 to 5, fundamental frequency should be equal to 1. Okay, so we're going to change that to 1. We're going to calculate our An. Okay, it's all zeros, and this time I'm still going to use the 100 coefficients. Okay, and this is my Bn. Okay, so after running those couple of lines, notice that if I go length of An, it's 100. Length of Bn is also 100. Okay, so there's 100 coefficients inside the vector An and Bn. And A0, I don't think I declared that, so I better do that now. A0 is equal to 0. So let's do that. Okay, so A0 should return 0. That's fine. Okay, so given that, let's continue and evaluate the function. Okay, so there it is. Let's label it and do all the other things as well. Okay, so you see the red line is the theoretical. So that's basically a reconstructed, or one that I built to represent the original signal here over one period, okay, between 0 to 1. That's basically the red line. Okay, and the blue line that has the ripple, that's your Fourier series, containing, of course, Fourier series using 100 coefficients. Okay, that's what we see here. Okay, now I can choose some other value. So, well, firstly, let's seeing this, it verifies that we've done it correctly because the shape is good. Okay, it basically matches quite well to our theoretical. Okay, so let's see what happens if we reduce the number of coefficients that we're using. Okay, so for example, instead of using 100, I'm just going to use 5 coefficients. What do you expect to happen? Well, when the number of coefficients go down, what you're, let's get rid of that. No. Okay. Something's not right. Let's have a look. Okay, something's not right. I'm going to have to go in and dig this line out. I'll follow up on a later video.